Okay, yesterday we started our discussion on uh, load multiple and store multiple instructions. So we understood the advantage of load multiple and store multiple instruction. So it is much more efficient than compared to the single register transfer instructions. So because in one, just by writing one instruction, it is possible for you to load multiple registers, and just by writing one store instruction, it is possible for you to store the content of multiple registers into the memory locations. But at the same time, this also has a disadvantage, and the disadvantage is that it increases the interrupt latency, and that is justified using this. Okay, so many clock cycles are required before the processor can pay attention towards the interrupt. Okay, and then we went through the syntax of load multiple instruction and store multiple instruction, and then we understood the different addressing modes, IA, IB, DA, DB, all these things, and then a few examples with respect to that. So that is what we understood. Now we'll see the working examples on the same now. So here I'm taking the example of load multiple with the addressing mode increment after. Okay. Now if you just observe here, I have the table defined in my code memory. So with the data 4441113332222. So I'm writing this LDR R2 comma equal to C value. So that is I'm loading the starting address of my table to the register R2. So then my intention is to load the content of all this memory location to my destination register R3 to R6. Now I'm using LDM IA increment after, and then the base register with the write back. Okay, because I have the exclamation also used, base register R2 with the exclamation, which is nothing but the write back. So this base register R2 is holding now the address of my table, C value table, starting address of my C value table. Now what it will do? So first, since it is increment after, first it will load this 4444 into the first destination register R3. Next 111 gets loaded into the next destination register, that is R4. 333 gets loaded into the next destination register, that is R5. And finally, the last thing 222 gets loaded into the destination register 6. So now this R2 again gets incremented by 4 more bytes since it is increment after, and R2 will be pointing to the next memory location. Okay, so this is what the example we have now for execution, and I've put the table also here just to show you that the starting address is from this. Okay, this gets loaded, next this, and next this gets loaded, and the ending address is this. Okay, the last element that got loaded into the last destination register is this, but Rn value is 4 bytes more than the last value that gets loaded into the last destination register. So 4 bytes more than the address of the memory location to which the last destination register loaded. Okay, so it is 4 more than that. So and that is what is, and then I put the table also to show you that. So now let us perform the execution of this, and we will see how these values, so they all get loaded into these registers. So just by writing one instruction, one load multiple instruction. So I'll copy this. I'm replacing it. Let me save. Translate, build. Now we'll go for debug. So C value. So I'm loading. So I have taken it as name as C value because these are all the values which are there in the code memory, and so I've taken it as code C value. C value is nothing but code value. Okay, so now 0 is 3, 0C is the memory location from where my table is starting. Okay, let us go to the other memory window and let me put 0C. So these are my data. Okay, 444, 111, and 222. Next, what I'm doing, so LD, and in R2 I have the register. Sorry, in R2 I have the starting address of my table, that is 000C. Now LD MIA, okay, what it will do? It will take the content of this base register, and that is what this is what the data that is present at that particular address, and 444 gets loaded into the register R3 here. 444 will come here, and next 1111 comes to the next register, and 3333 comes to this register R5, and 222 gets loaded into the register R6, and finally R2 will be holding the address of this particular memory location. Okay, so you can just count. Now this is 0C, this is D, E, F, and this is 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and after 19 it is um, 1A, 1A, 1B, and this is 1C. This memory location is 1C. Now, after all these elements got loaded into this destination register, so the final value that you'll be seeing inside the register R2 is 1C. Okay, 1C will be the content, but the last memory location that got loaded to the last destination register is this 222. So that is the reason we say -4 here. Okay, -4. Is that clear?
Yes, sir.
Now I'm pressing F11. Just observe R3 to R6 now. See, R3 to R6. So R3 is loaded with 444, R1 is loaded with 111, R3 5 is loaded with 333, and R6 is loaded with 222. And what about R2? See, is pointing to this particular memory location, that is 1C. 1C is the address of this particular byte. Okay, so this is the execution. So what I wanted to show you people. So next we'll move on to the next example. So in the next example, so what I've used is increment before. So okay, this using this example, we are trying to understand the increment before example. See, everything is same except this IA, we have changed it to IB. That's all, and the rest all is same. And again, this is with the write back. Now what happens here? Let us just analyze this, and then we'll go for executing. So we're loading the address of my C value to the register R2, and then I'm just trying to load all these things to my destination register R3 to R6. Now what will happen now? So since R2 is the address of the first element and it is increment before loading the first destination register, so with the content of the memory location whose address is present in R2, it will go for incrementing this R2. R2 gets incremented by 4 bytes. So now R2 initially was holding the address of this particular memory location. Right now R2 is holding the address of this memory location because it is increment before. Now what gets loaded into the register R3 in this example is not 444, it is 111. 111 gets loaded into the register R3, 3 gets loaded into the register R4, 222 gets loaded into the register R5, and the next location, I have not written that over here, okay? So the next memory location, so something there, either it might be 0 or some other junked value, and that gets loaded into the register R6. So hope that is clear.
Yes, sir.
Yes, sir.
Okay, now we'll I don't have to copy this because only one change that we need to do is here. So instead of this IA, we got to make it as IB, and the rest all is same. Changing it to IB, we'll save it, translate, build. Okay, now again set the 0C because we didn't do any major changes to the program except this IA, we changed it to IB. Okay, so again still the address of my C value is same, that is 0C, and these are my data. Now if I press F7, what will happen is 111 gets loaded into the register R3, 333 goes to R4, and 222 goes to R5. So, and after that, what we have? So, in the memory location, this is the data we have. This data will go and sit into the register R6. Okay, and oh, sorry, yeah, R6, and then now R2, I've told it is again right back. So the last memory location that gets loaded into the destination register R6 will be this, and even R2 will also be pointing to the same memory location. So if I go back to PPT here, it's just after the second row here, see the end address and the RN value both are same. Okay, here it was -4, but it is now -4. That means the last memory location that gets loaded to the destination register and the address that will be present finally in the register RN will be the same. Okay, now I'm proceeding now. I'll press F11. See now. So what got loaded into the register R3 is 111, and what got loaded into register R4 is 333, and what got loaded into register R5 is 222, and observe now R6 is loaded with this value, and see the content of register R2 also, it is 1C. What is the address of this particular byte? So in the previous example itself we computed it, it is 1C. So this was the last thing that got loaded into the last destination register. Even RN is also pointing here only, and at the second row of the table is justified. Is that clear?
Yes, sir.
Okay, next we'll move on to the next example now. So next example is STMIA. So we had the first two examples on load, multiple, increment after, and increment before. So now we have the store multiple, increment after, and store multiple, increment before. Okay, first we'll see store increment, store multiple, increment after. This is the example I'm taking. Again, the same table. I'm loading the address of my table to the register R2, and then so first I'm loading them. Okay, LDM IA load multiple increment after. I'm loading these values to my destination register R3 to R6, and after that, so I have the data area also here in my program. Okay, so a little bit we have changed. We have the data area as well, and the memory location that is declared inside the data area, I'm calling it as D value. Why I'm calling it as D value? Because this particular variable is there inside the data area, and hence I'm calling it as data value. I'm loading the address of data value to the register R7. Next, STMIA store what increment after, and this is my base register now for this store. R7 is the base register for load, R2 was the base register, and these are my source registers. Okay, so for store these are the source registers, and for load these are the destination register. Now I have R3 to R6 loaded with the content of this data. Okay, R2, R3 to R6 is loaded with this data. The data which is available in the code memory gets loaded into the register R3 to R6. Now using the store multiple in increment after. So from this, the data which is available in R3 to R6 registers, I'm storing them into this particular memory location. So hope the example is clear to you people.
Yes, sir.
Okay, now let us quickly execute this as well. Okay, everything is fine, I guess. Yeah, so I'm saving it. So 0 errors and 0 warnings, building it. Okay, now we'll debug. Okay, now observe, I'm loading the C value address. So I don't think we get the same address now, because there is the modification in the code, because we have additional statements here. It should be more than 0C now. Yeah, I'm getting it as 1,4. Okay, so my C value data are starting from the address 1,4. Let me change it. My C value data are stored starting from the address 1,4. Okay, that is fine. Next, what I'm doing, I'm loading all these things into my registers R3 to R6. See, my register R3 to R6 is loaded with the data values which were there inside my code memory. Okay, next. I'm loading the address of my D value. Since D value is there inside the data area, the address that gets loaded into the R7 is 444. See, R7, sorry, 4 followed by 7 zeros. R7 is loaded with 4 followed by 7 zeros, and that I have here in my second memory window. So it is already there, 4 followed by 7 zeros. Next, what I'm doing, store multiple increment after. So take the content of the first source register R3 and put it into this memory location. So now 44, what is there in R3? 444. 444 comes to this particular memory location. And next 111 comes to this next memory location. And then 333 to this memory location. Next 2222 to this memory location. So now let me press F11. So just observe here. See? So these memory locations are loaded now. So hope it is clear.
Yes, sir.
Okay. Now, and again here also just to demonstrate that store increment after, same thing, it is justified. The first line is justified. So just observe the uh, R7. Okay, what it is. So it is pointing to this particular byte right now. So first it loads this, then gets incremented, loads this, gets incremented, loads this, and gets incremented. And R7 is right now holding the address of this byte. This 4 followed by 6 zeros and 1 0, what you're seeing, it is the address of this particular byte. Okay, now the next example. So in the next example, again, we have two things. One is store multiple increment before and load multiple decrement after. So two things are there. Okay, so we'll try to understand this. First, we'll try to understand here and then we'll go and execute. So now what I'm doing, so intentionally I'm taking the address of the data area here. I'm loading it into the register R0. That's fine. And then, so I'm taking the value 9 in the register R1, 8 in the register R2, and 7 in the register R3. And then what I'm doing, so the content of this register R1 to R3, what I have, I'm storing them into my data area. So you see, store multiple, increment before it is, increment before. So from this 4 followed by 7 zeros, and these are my source registers. So since I've used increment before, so where will the first source register, that is R1 content is 9 right now, what memory location this 9 gets stored? Is it stored at the address 4 followed by 7 zeros or 4 followed by 6 zeros and a 4? Where it gets stored? It is increment before. In R0 we have the address 4 followed by 7 zeros. Now where this 9, data 9, which is there inside the register R1 is going to get loaded. Which memory location?
4 with 7 0 and 4.
4 with 6 zeros and 4. Okay. 4 followed by 6 zeros and a 4. Okay. Next. We have this next 8 getting loaded into the memory location 4 followed by 6 zeros and 8, and we have this 7 getting loaded to the memory location 4 followed by 6 zeros and a C. Okay, so that is how. So we are storing all these things to the memory location starting from the address 4 to 12. Next, in R1, after I store these things to the memory location, now I'm loading different values to R1, R2, and R3. So what is the value that I'm loading right now to the register R1? I'm overwriting the content 9 by 1, and in R2 I'm overwriting the content 8 by 3, 2. In R3 I'm overwriting the 7 by 3. After that I'm doing load multiple decrement after. Decrement after in R0, what is that you have? Can you just tell me?
It is pointing to the data 0007.
Yeah, pointing to the data 0007 present at what address? C.
4 followed by 6 zeros and C.
Yeah, very good. 4 followed by 6 zeros and a C. Now, this is decrement after. Now, what will happen? See, whenever you take decrement, see, whenever it is IB or IA, so this is your first source register. This is your first register. Whenever it is decrement, okay, decrement after or decrement before, so this will be your first register. Okay. Now what happens now? R0, as you all of know, it is pointing to this 7. Okay. Now this 7 gets loaded into the register R3. This is what is important here. When it is decrement after or decrement before, so it is in the reverse order. First this gets loaded. Okay. Now R3 will get the value what? Will get the value what?
7.
7. So why I'm putting 3 here? Because this 9, 8, 7 was already there. Now if I execute this, I won't be knowing whether this register 7, R1, R2, R3, whether they're updated from the content of these memory locations or not. I won't be, it's not possible for me to visualize. Okay, but gets updated, it overwrites. 7 is overwritten with 7 itself. You cannot note this. And 8 gets overwritten with 8 itself. And 9 gets overwritten with 9 itself. Now just to visualize it, what I'm doing after loading these things into this memory location, I'm intentionally loading some different values to these registers. Now when this statement is executed, you can see that the value 3 which was there in the register R3 is overwritten by what? 7. And next 8 gets loaded into R2, and your R1 gets loaded with 9. That means you're restoring the original values for R1, R2, R3 from the memory back. Okay, people understood?
Yes, sir.
So when you're writing a very big program, large program, so it may not be sufficient for you to use the 16 registers or the 15 registers that are available. So that time what we do, so in case say I want to make use of the register for some other purpose, so these register contents I'm backing up to the memory now. So this was the content 89987. I don't want to lose this values. What I do, I store them into the memory because memory is bigger. You can store them into memory, use the register for some other purpose, perform the operation, and restore the values back to the register. Okay, the values which are stored are backed up to the memory, so bring them back them into the register. So this is the kind of operations which we use, especially when we're writing a much bigger program where we are using a lot of registers. Okay, but the programs what we're writing or what we wrote all these days, so were not such a big program, and they were all small programs, and even we have not made use of more than 4 to 5 registers. So all our register usage was within 4 or to maximum extent to 5 registers. That's all, not more than that. In case if you there is a need for you to make use of or utilize all the registers, and if you want to do this repeatedly, so then this is the kind of operation that we perform. So what is this operation? We call it as, so backing up the content of the register to the memory location, and then using the register for some other purpose, and then restoring the content back to the registers and resuming with the original operation. Hope you understood?
Yes, sir.
Okay. Now we'll quickly perform the execution of this. And even so, you cannot have say I have written Python programs are is there unlimited number of registers? No, same registers. I have written Java programs are will for Java program do I have unlimited number of registers? No, same thing. Now anything which you write, there is something called as compiler and interpreter. So it is the responsibility of your compiler and interpreter to generate a code appropriately such that everything gets executed smoothly by using the limited resources. So, but normally when I'm writing the Python program, I don't think about the registers. And normally when I'm writing the Java program, do we think about the registers? No, our focus will be only on declaring the variables. Any number of variables we declare. Correct? We keep declaring the variables and we keep on writing our programs. And ultimately when you compile your Java program, it is the responsibility of the compiler to take care of that. So the object code or the machine code that is generated, so is in such a way that it uses the available number of registers. In case if those are not sufficient, so then appropriate backing up of the content of the registers will be taken care by your compiler. But so as a programmer, you have written C programs all these days. So were you thinking with respect to the availability of registers? No, that is completely hidden from for us. So we keep just declaring the variables and we start writing our programs, but we never think of the registers. Even all these days, you people were not knowing how many registers are there. Okay, all these things. So most of the things, these high-level programming languages are masking. Okay, and the entire responsibility is taken by the compilers which we use. So let us execute this. So I've overwritten this. Translate. So it is saying me one error. So oh, end directive is missing. I think I forgot to copy that. End. Okay, now 0 errors and 0 warnings. Build, debug. Okay, so now let us start. See, R0 I'm loading with 4 followed by 7 zeros, which is the address of this particular byte. And now in R1 I'm putting 9. In R2 I'm loading the value 8. In R3 I'm loading the value 7. Next, all this data which is here 8 9 7 8 I'm loading into from these registers. I'm loading into this memory location, storing it. Not, don't say it as load when you're writing to the memory, it is store. Okay, storing them into this memory locations. So I'll press F11 now. See, so got loaded. So my what was my first data? 9. So 9 is loaded. Okay, and since I used increment before, see this, it is not loaded here. So the first 32 bit is empty. OP people are following?
Yes, sir.
Yes,
So
sir.
this memory location is empty and we have 9 loaded from here and then 8 and then 7. Next, what we're doing, intentionally we were overwriting the contents of our registers R1 to R3. I'm changing R1 from 9 to 1 and R2 from 8 to 2 and R3 from 7 to 3. So this is one. Now I'll restore their original contents back by writing LDM decrement after it is. Now if you just observe R0, R0 is what right now? So 4 followed by 6 zeros and a C. So what address is this? It is here. Okay, and what we are using is decrement after. So first it will load this 7. See what register? So 7 will not go to your register R1. Okay, so when it is decrement after or decrement before, it is in this direction. OP people are following?
Yes, sir.
Okay, so see the 7 the content of this memory location, that is 7, will not go to the register R1, it will go to the register R3. Just observe R3 now. So R3 will be overwritten, so this 3 will be overwritten by 7 now. See, R3 is 7. Okay, so that is, so when it is decrement after or decrement before, the last register is your first register. Okay, and the first register is your last register. Next, what's happening? 8 gets loaded into the register R2. See, 2 will be overwritten. Yeah, everything finished. So 7 got here, 8 got here, and 9 got here. And what was the initial status? So 8, 9, 8, 7, and 9, 8, 7. You got it. So hope it is clear.
Yes, sir.
So these are all the small examples, but later on when you're writing the big programs and if you have the scarcity of the resources, registers, so then how to handle them? So by using these things. Okay, so these are all the simple things which are very much essential for you to write a much bigger program, which which is going to use all the registers. Okay, and the scarcity of the registers can be avoided by using this simple technique or the logic. So what we are doing now, we are doing it here by ourselves. So since we are writing a very low level program and which is very close to the compiler, but when you're writing the high level programming language, so the burden is more on the compiler and it's going to take care of all these things. Okay. There is one more subject called as system software. So I don't know whether I think you'll study that in 6th semester. So and again there you'll understand how your high-level programming language gets converted into the low-level code or the machine code. So 1 pass assembler, 2 pass assembler, all these things will come. So that is again you understand more in the system software subjects regarding this. So what we are discussing is directly at the lower level. So when you go to the system software subject, when you're studying that, so you'll understand how your program which is written in high level language, either it could be in C or Python or Java, how it gets translated into the machine code. Okay, so that you'll get few problems on that, one pass assembler and two class assembler. So if you understand those problems, you'll get an idea, complete idea how the things are happening. And that is not required for us now. How one pass assembler works and two pass assembler works, that is not required for us. Next, uh, is it the other example? Yeah, this is another example. Now what we have now is the same example. Instead of decrement after, what I'm using is decrement before. Okay. Can anyone tell what could be the output of this program? What are the values that you're going to see in the register R1 to R3? This all is same. Even it was IB increment before. So even this is also increment before, and only the change is this. Instead of decrement after, we have taken it as decrement before. So can anyone just tell me what could be the output of this? What are the values that you're going to see in the register R1 to R3? What is the value that you're going to see in the register R3?
8.
8. Very good. And then in R2,
8, 7, and
9.
0.
8.
In R1, you'll see 0. In R1, you'll see 0. In R3, you'll see the value 8. This is skipped now because it is decrement before. So in R3, you'll see 8. In R2, you'll see 9. In R1, you'll see the value 0. No, not this 0. So in the memory location 4 followed by 7 zeros, there will be 0 because we keep writing this from the next location. So R1 will get loaded with 0. So now this I need not copy. So we will modify this itself. Now I'm stopping this debug. So this will change it to db, decrement before. Okay, so let us execute. So stored, so the stored into the memory location. Now intentionally changing the values of R1, R2 and R3. Now LDM Now what will happen? See, so we have 7 skipped now. So 8, 9, and we have R1 loaded with 0. And what is that 0? This memory location. So hope it is clear.
Yes, sir.
Okay. So next is stack operations. So till now you understood how to perform multiple load and how to perform multiple stores just by writing one single instruction, and what are the different types of addressing modes that you can use within store multiple and load multiple. Okay, so next thing is to understand how to perform the stack operations. So can we have the stacks in the ARM? Yes, it is possible. Even in stacks, you understood stacks in the previous semester in the data structure subject. The same stacks can be implemented even here in the ARM also. Now, but here the ARM architecture, in order to implement the stacks, so what it uses is important. So in order to implement the stacks, the ARM architecture uses the load and store multiple instructions to carry out the stack operations. If I ask you what are the stack operations, all of you know. So push operation and pop operation. These are the two major operations that we perform on the stack, push and pop. Now, how do you perform push and pop operation within the stacks of the ARM architecture? So it is by using the load and store multiple instruction. Okay. Now to perform the pop operation, okay, so that is, you know, that what is pop operation is removing the data from a stack is called as pop operation. Now how this pop operation is performed in ARM architecture stack? It is performed by using the load multiple instruction. Now where is a stack? Stack is basically the memory. Okay, stack is in the memory. Now when I say remove the data from the stack, you got to make use of the load instruction. So that to not single register load instruction, multiple load multiple instruction, that is LDM. So using LDM, you can go for getting the data which is there in the memory and load it into the some register. Okay. So and similarly, how the push operation is performed. To perform the push operation within the stacks of ARM architecture, you got to make use of store multiple instruction. I guess the concept is clear.
Yes, sir.
Yes,
See,
sir.
where is the stack? Stack is there in the memory. Now, if I want to add something to the memory, which instruction will use? What is the instruction that adds the data to the memory? What is the only instruction that adds memory data to the memory?
Store instruction.
Store instruction.
Store.
And we are not. And again, store also there are two types: store single register and store multiple. Yes or no? Which one we make use? Store multiple. So it is not str. We make use of stm. Hope you people are following.
Yes, sir.
What is str? Store register. What is stm? Store multiple. Okay, so we make use of store multiple. And similarly, when you want to remove the data from the stack, we make use of LDM. Okay, so LDM is the instruction that we use. Load multiple is the instruction that we use. Now, okay, now you understood how the stack operations are performed within the ARM architecture by using load multiple instruction and by using store multiple instruction. By using load multiple instruction, you perform the pop operation. By using load store multiple instruction, you perform the push operation. Now, again, so you can define two types of stacks depending on how the stack is growing inside the memory. Okay, so one is ascending stack, another one is descending stack. If the stack is growing from the lower memory address towards the higher memory address, then I say it is an ascending stack. If the stack is growing from the higher memory address and towards the lower memory address, then I say it is a descending stack. Say, for example, let us come here. So this is my memory. See, if I store the first element here and the next element here and the next element here and the last element here and one more element here, which is my top of the stack? This is my top of the stack. Yes or no?
Yes, sir.
Now,
Yes, sir.
now how in what direction my stack is growing? Is it growing from lower addresses towards the higher address or higher address towards the lower address?
Low to high.
Low to high. Now this is called as an ascending stack. And similarly, say for example, I start stack from here. Okay, the first element is added here, and the next element is added by decrementing the memory address. Say it is added here, and again I decrement the memory address and I add here. So then now stack is growing from the higher address towards the lower address. This is what we call it as a descending stack. Okay, so based on how the stack grows, there are two types: ascending stack and descending stack. Okay, so ascending stack we normally represent it by using A, and descending stack we represent by using D. Okay, that's fine. So now you understood here in this slide. So ARM architectures, they support the stack operations, and the pop operation is implemented by using load multiple instruction. Push operation is implemented by using store multiple instruction. And based on how this stack goes, there are two types of stack: ascending stack and descending stack. Now, okay, done. Then, okay, based on how it grows, two types. Based on where the stack pointer or the top. So in the previous semester, we used to call it as the top. The pointer which points to the top of the stack, we used to call it as the top. And usually it is the stack pointer. You can call it as a top, or else you can also call it as a stack pointer. Based on where the stack pointer is pointing, again, two types of stacks are possible. One is full stack, another one is empty stack. So full stack is represented by F and empty stack is represented by E. Now, what is a full stack? If the stack pointer or the top is pointing to the last item on the stack, okay, or if it is pointing to the most recently inserted item onto the stack, then we say it is full stack. Let me write and show you. So this is a stack. So I've inserted 1 here, 2 here, 3 here, and 4 here. This is my most recently inserted element onto the stack. And if if top or SP, let means that we will not call it as top here, we'll call it as SP, stack pointer. So if SP is pointing to this, if SP is pointing to the most recently inserted element, then I call it as a full stack. Hope you people are following.
Yes, sir.
Yes, sir.
Then what is an empty stack? Say for example, let me write. So 1, 2, 3, and then 4. Okay. Now say the stack pointer is pointing to the next location after the most recently inserted item. Okay, then I call it as an empty stack. So stack pointer is not pointing to the most recently inserted element, it is just pointing to the next empty location after that. Now this I call it as an empty stack, and this I call it as a full stack. Okay, don't be under the impression that an empty stack is a stack without any elements. See, I have elements 1, 2, 3, 4. These are the elements, but so this empty, we call it as an empty stack based on the stack pointer where it is pointing. Right now, the stack pointer is pointing to the just an empty location, which is just after the insertion of the last element. So points after the last item on the stack. Hope you people are following.
Yes, sir.
Okay, now, so let me write a few stacks. You just answer me. Okay, now based on this full stack, empty stack, ascending stack, and descending stack, so we can define 4 types of stacks now. One is full ascending stack, full descending stack, empty ascending stack, empty descending stack. Okay, hope you people are able to understand.
Yes, sir.
So 2 types of stack based on how the stack grows. 2 types of stacks again based on where the stack pointer is pointing. Now if I combine these two, so totally I can define 4 types of stacks. So full ascending stack, full descending stack, empty ascending stack, empty descending stack. So I'll write few examples now. Now this itself let me take. Okay, let me write the address as 1000 here, and this is 2000, and this is 3000, and this is 4000. So can you tell me what stack is this right now? What stack is this? Is it a full ascending stack or full descending stack, empty ascending stack or empty descending stack?
Full ascending.
Full ascending. Good. Now let me take this again. Let me write the same addresses: 1000 here, 2000 here, 3000 here, 4000 here. Now what stack is this?
Empty ascending.
Empty ascending stack. It is an empty ascending stack. First you observe where SP is pointing. SP is pointing to the next empty location of the last item inserted, and the addresses are increasing. Okay, now this is an empty ascending stack. Now similarly, if I want to write the full descending stack, how do I write? Ulta breathing. So I write like this. Say this is my address 4000, and this is the next 3000. So 1 I have, 2 I have, 3 I have here, and say this is 2000 address, and 4 I have here. So this is 1000 address, and stack pointer is pointing here. SP is pointing here. Now what stack is this?
Full descending.
Full descending stack. And if I make my SP point just after the last item that is inserted here, it becomes empty descending stack. Empty descending stack. Hope you understood.
Yes, sir.
Yes, sir.
Okay, now, so this table now you can easily understand. So now within the stack operations, in earlier when we understood load multiple and store multiple instruction, so these are the addressing modes that we understood. Decrement after, increment after, decrement before, increment before, and similarly for store also we understood these addressing modes. So increment before, increment after, decrement after. Now, when you're using this load multiple and store multiple instruction to perform the stack operations, we make use of other 4 addressing modes. Now, what are those 4 other addressing modes? It is full ascending stack, full descending stack, empty ascending stack, empty descending stack. Okay, so along with these 4 addressing modes, we have 4 more addressing modes. What are they? These things which are used for performing the stack operations. See, addressing, so I wrote on this, let me erase. See, addressing modes for performing what? The stack operations. These are the 4 addressing modes which you can use along with store multiple and store load multiple instruction to perform the stack operations. Hope you people are following?
Yes, sir.
Okay, now how do I perform the pop operation from a full descending stack? So like this, LDM FA. Now I want to remove the elements from a full descending stack. What is the instruction that I make use of? You already know it is LDM, load multiple instruction, that you have to use. But what is the addressing mode? So I want to pop out from the full descending stack. So the addressing mode that you got to make use of is FA. So load multiple full ascending. Okay, and similarly, I want to perform the pop operation on a full descending stack, LDM FD. I want to perform this pop operation from a empty ascending stack, LDM EA. I want to perform the pop operation from the empty descending stack, LDM ED. Hope people understood this?
Yes, sir.
Yes.
Now, this LDM FA, it is equal to this, same as this. LDM FA is same as LDM DA. And LDM FD is same as LDM IA. LDM EA is same as LDM DB. So LDM ED is same as LDM IB. So when you're free, you sit and try to analyze. They're exactly the same. Only thing is, when I'm performing the stack operation, I use these addressing modes. Okay. And similarly for push, you see. So I want to push the elements onto a full ascending stack. So this is what the instruction I make use of. So I want to push the elements to a full descending stack. This is what full empty ascending stack. This is what I use. Empty descending stack. This is what I use. And these things are exactly same as these things. Correct, right?
Yes, sir.
Okay. Now I have the examples here. So this is okay. All these things you have understood. Now we'll focus on this now. So this is what the precondition. So before execution, this is what I'm assuming. This is my stack. Okay. So you can just observe here. So this is address 18 and this is address 14 and these are empty locations. And what is the address? Address is decreasing. So 18 to 14, 14 to 10 and 10 to C. Okay. So this 18 in decimal you can find out. And this 10 in decimal is 16. Okay. 16 plus 4 is, I think this is 20 and this is more than that. Now the various stack pointer is pointing here. Now can you just tell me what type of stack is this? Look into this and tell me.
Full descending.
Yeah, it is a full descending stack, FD. It's a full descending stack. Okay, now I want to say this is what the content I'm assuming. Now SP, where it is pointing to this 80014 address. SP is this. And in register R1 I have 2 and register R4 I have 3. Okay. Now I need to push these two now. I need to push these two constants 3 and 2 to my full descending stack. And what is the instruction I write? Just observe here. So store. So it's a full descending stack. I got to know that this is a full descending stack. Now how do I perform the push operation to the full descending stack? STMFD. And then where is my base register? SP is my base register. This register is acting my base register. And whose content I need to push? The content of the register R1 and R4. See, when it is the range. So if there are multiple registers, then you put an hyphen here. So to specify the range. Now when there are only 2 registers, you can put comma. Okay, people are following?
Yes, sir.
See, so here if you just put hyphen, what will happen? It will take the range R1, R2, R3, R4. So that is wrong. Now I want only these 2 registers to be pushed. So R1, R4. Now see, observe the status after this STMFD is executed. See, so the 3 register R4 is pushed here. Okay. See, whenever it is decrement, okay, full descending, right? Decrement, it is in reverse order. R4 is taken and pushed here, and then R1 is taken and pushed here, and CSP is pointing to this. OP people understood?
Yes, sir.
Okay. Now another example. So this is empty descending. So this is full descending, and what we are discussing now is empty descending. So this is the precondition now. Okay, but the precondition stack I've written. So this is, sorry, this is my pre-status, and the stack is shown here. So R1 I have 2, R4 I have 3, and SP is pointing to 10. So SP is pointing to 10, and it is where it is pointing. It's pointing to the next location after the last inserted element. Now this is empty descending stack because the addresses are decreasing. Okay. Now, so STM ED is the addressing mode that you need to use. And then SP, then R1, R4. So after that, you just observe the status. Now this was the most recently inserted one, and where we have now SP is pointing to the next empty location after the most recently inserted one. Hope you understood.
Yes, sir.
So this is the graphical representation of the post condition after execution. Okay. Okay, now I have the working examples also here, popping one at a time, and these are all the examples. We got to execute them and see the output. So we'll stop here. So let me see how many slides are remaining. In the slide number 88, last is 1110. So I think another 2 classes are sufficient. So in 2 classes, I can complete the module 2 also. Okay, so this execution and the remaining slides, I think 90, almost 90. The remaining 20 slides are there. So so 1.5 class, I think, is sufficient. So we'll complete, no issues, no worries. So I'll start. Any doubts?
No, sir.
Okay.